Good morning, friends. If you recall, we were trying to find out the expression for those partial derivatives which were required to model the perturbed aerodynamic forces and moments. And if you recall, this was expanded as Fax by du by u1 to u by u1 plus dFax plus d alpha into alpha, like this. Similarly, this was dFax Az by du by u1 to u by u1 plus dFaz by d alpha into alpha, and then q terms, alpha dot terms. And similarly, for pitching moment, we expanded it like this: dm by du by u1 into u by u1 plus dm by d alpha into alpha plus terms with q, alpha dot, and delta e, right? We have so far completed these u derivatives. The expression for u derivatives are known, and we realize that if I know the aerodynamic characteristics, then I will be able to find out the values of these derivatives: dFax by du by u1, dFaz by du by u1, dm by du by u1. And we also realize this has to be evaluated at steady state. And also, very importantly, we should not forget we are using stability axis system. Because the perturbed equation of motion were simplified using stability axis system. So it is important we again try to understand what is a stability axis system. Let's say this is the airplane. And this is body axis X, Y, and Z. This is the center of gravity, and there's a wing. This is XYZ is the body fixed axis system. The alignment of X is along the fuselage reference line or some symmetric line. However, now once we talk about a stability axis system, we have to understand one thing very clearly. What is that? Let us understand. This is the airplane. Let's say at steady state, let's say this airplane is flying at a speed v. Is the relative airspeed. The airplane is going like this with the angle of attack, and the direction of its relative airspeed, so we have shown it like this. This is the condition at steady state. This is important. This is at steady state. We define stability axis system in steady state only. That is, what we do, we said, now my x orientation will not be along any symmetric line, not that fuselage reference line, or a line where the product of inertia may vanish. But what we are saying, the x is now aligned with the direction of velocity, along the direction of velocity, right, in the vertical plane, right? And this is xs, and this gentleman then become zs. So if we now try to see what exactly it means this angle earlier, this was alpha angle of attack at steady state. That was the velocity vector, angle between velocity vector and the x-axis. That is how we define angle of attack. And when I am saying that, we are also assuming that x is aligned along the chord line of the wing. However, when I am defining xs like this, then I know that there is no angle between xs and v. That is very important. What is the implication of that? You see, if I am using x, y, z axis system, then there will be u and there will be w. That is, the component of v along x direction is u, component of v along z direction is w. They are non-zero if there is a alpha 1, right? I am restricting my discussion motion in the vertical plane. Right? However, once I am taking xs, ys, and zs axis system, which is stability axis system, now you know that u, that is the velocity along x direction, is u, or the v, total velocity v, in the vertical plane. Right? And there cannot be any component of this total velocity along a direction perpendicular to xs. So along zs there won't be any component, so we say w1 equal to 0. And this v is the v total, which is nothing but u along the stability axis system. Correct? So the advantage we get is that w1 is 0 when I am using xs, ys, zs. So what is important thing is that I am defining stability axis system at steady state. That is, I find what is the angle at a steady state, and I align the x-axis along the velocity vector so that there is no component of total velocity along zs axis. I'm simply, if I'm flying like this, and this was my x-axis, and this was the velocity vector like this, so I'm just aligning this x-axis along the velocity vector. So that is why w1 becomes 0, and this orientation is done only referred to condition at steady state. That is very important. Now we are talking about perturbation. So what do? We will give some perturbation and see how this diagram to be interpreted. So we have no objection that this is alpha 1, this angle, and we have, there is some disturbance that has happened because of the total velocity has changed from the steady state velocity, and let the component here is, earlier it was u1 at steady state and plus u is resolved along zs xs axis. This is the xs axis. This is this small disturbance which is perturbed alpha. Okay, clear? What is the message? This was my total velocity u, because there was no jet component. Now because of perturbation, there is a perturbed angle of attack has come, and this direction is the total velocity after perturbation. So this is perturbed angle of attack, and the small u is the perturbed speed along xs direction. So it becomes u1 plus u, and the lift or the CL and CD will be along and perpendicular to the current direction of V, which is after the perturbation. Okay. So this has to be understood, and of course along this direction this will be small w, which is the component along zs axis. Please understand, this w is a perturbed quantity. At steady state there was no w component along zs, but because of perturbation the velocity vector has changed, so there will be a w along zs direction, which is a perturbed quantity. Right. Once I do that, I can always use this advantage. I can write Cx is equal to minus Cd cos alpha plus Cl sin alpha, and we know that we are talking about small perturbation because this alpha is perturbed angle of attack. So for small angle I can write Cx is equal to minus Cd plus Cl into alpha. Remember, this is small perturbation. Similarly, I can write Cz is equal to minus Cl cos alpha minus Cd sin alpha. You can refer this diagram, and for a small angle I can write this as minus Cl minus Cd alpha. So there are two equations which will be very handy. We will be using this. So I thought before we use these equations, we again reiterate what is our understanding about stability axis and what do we mean by perturbation about steady state. Right? This, I presume, is clear with you. Now after these u derivatives were over, we will now focus on the alpha derivative. So what we are going to do? We want to derive expression for alpha derivatives. Let me start with df ax by d alpha, although we will be doing all the things. Let me write that also, and dm by d alpha. Primarily these three partial derivatives will be derived in terms of aerodynamic coefficients, right? So let me start with dfx by d alpha. So let us take dfax by d alpha, and the procedure is similar to what we write. Fax is q bar scx. So dfax by d alpha will be equal to dcx by d alpha into q bar s. But we know that we have to derive this expression dfx by d alpha at steady state. So at steady state, dfax by d alpha will be dcx by d alpha to be evaluated at steady state, and for q bar we write q1 s. What is this? The initially when you wrote q bar is what? Q bar was half rho u1 plus u whole square plus v square plus w square. All the perturbed quantities also included here. But when I write a q1, I am evaluating this at steady state, which becomes q1, and steady state, this is 0, this is 0, this is 0. So only it is half rho u1 square, and which is equal to half rho u1 square, which is equal to q1 bar. 1 is for steady state condition. So we have written this, as simple as that. So we need to find out what is dcx by d alpha. So what we will do, we will use this expression. What we know, cx is equal to minus cd plus cl into alpha. So dcx by d alpha will be minus dcd by d alpha plus alpha into dcl by d alpha plus cl. This is clear? Now tell me, what do you want to find out? We want to find out dcx by d alpha at steady state. So how this right hand side will get modified? Before doing that, let us ask ourselves, what is this alpha? Alpha is the perturbed angle of attack. So when I am evaluating at steady state, perturbed angle of attack is 0. So this gentleman goes off. So I get at steady state, this is minus dcd by d alpha plus cl, but cl what? Cl at steady state, so cl1. So what do you get? The expression of dcx by d alpha as minus dcd by d alpha plus cl1. So dfax by d alpha becomes minus q1s. Or I don't take minus here, I add q1s dcx by d alpha, so it is minus cd alpha plus cl1. This is the expression. So now we see dfax by d alpha as q1s minus cd alpha plus cl1. So try to understand what is the meaning of cd alpha. What is cd alpha? dcd by d alpha. What is the meaning of that? How do I find that? You recall, drag polar is given by cd equal to cd naught plus k cl square. So I can easily find out dcd by d alpha as cd naught, if I assume it's constant with angle of attack for small angles. This will be 2k cl into dcl by d alpha. So this will be 2k cl into CL alpha. So you could see easily that I can find out value of dCd by d alpha if I know what is the aspect ratio of the wing, because K is nothing but 1 by pi aspect ratio E. If I know what CL this gentleman is cruising, because these are evaluated at steady state, CL1 will be given by CL equal to what? Lift equal to weight. So CL equal to 2W by rho V square S. So CL1 you can easily find out from this expression corresponding to the steady state, corresponding to the cruise, which is our steady state condition. Right? So simple to understand this. So once I know dfx by d alpha, we will now try to find out dfaz by d alpha. So let us find out dfaz by d alpha. Again, mechanically you can follow faz equal to q s cz. So dfaz by d alpha will be q1s dcz by d alpha, but we have to evaluate this at steady state. So the q will become q1, and this has to be evaluated at steady state. And for the steady state, I am using the notation 1. Which similar thing we did for dfx by d alpha also, nothing new. There I wanted to have an expression of dcx by d alpha. Now here dcz by d alpha. So again we go here. What is cz? Cz is nothing but minus cl minus cd alpha for small angle approximation. So you can find out dcz by d alpha with minus dcl by d alpha minus cd minus alpha into dcd by d alpha. Simple derivation. I am just taking a derivative both sides with respect to alpha. So dcz by d alpha at steady state, this becomes cl alpha minus sign at steady state minus cd1, and this, because at steady state alpha equal to 0, so this goes. So this is minus cl alpha minus cd1. This is dcz by d alpha. I can remove this alpha 1. Cl alpha is Cl alpha, lift up slope of the whole airplane. So once I know this, then dfaz by d alpha will look like this: q1s into minus Cl alpha minus cd1, and in textbook you might have seen minus is taken outside, and this is written as Cl alpha plus cd1. Now the question comes, what is cd1? cd1 means drag coefficient cd1. cd1 means drag coefficient at steady state, and for our case steady state is the cruise. I know that thrust equal to drag, and you know drag it can be written as q1s cd, and cd1 will be cd0 plus k cl1 square. So I can easily find out cd1 if I know drag polar of the airplane, and if I know at what CL the airplane is flying, which I always know from the fact that lift equal to weight gives me CL equal to 2W rho V square S. So simple, right? So you can find out dfaz by d alpha. What do you need to know? What is the lift off slope of the airplane? What is the CD at steady state? That is, what is the drag polar? And I know that from drag polar, what is the dynamic pressure at steady state I am flying? That is the altitude and the speed and area of the wing. As simple as that, right? So this also we know how to do it. Now the last part we will do dm by d alpha. Now we will be trying to find out derivative dm by d alpha, which is very, very straightforward. You know, m I can write as Q bar S C bar Cm. So dm by d alpha, which is partial derivative, will give me dCm by d alpha. And when I evaluate this at steady state, this has to be evaluated at steady state. This becomes 1. So this will become Q1 bar S C bar Cm alpha. Cm alpha. And what is Cm alpha of the airplane? What is Cm alpha? What brings to your mind when you see Cm alpha? Recall static stability? When we plotted Cm versus alpha, we said there is a requirement of this airplane to be statically stable about a trim, that the slope should be negative. So dCm by d alpha should be less than 0. So this is the condition for static stability, right? So typically this value will be negative, and you know that also you cannot go on making this more and more negative, because more stable means difficult to control. So there are typical values, typical range of values the designer will select for an airplane to have adequate, comfortable static stability, okay, which are known. Absolutely, from the configuration you can find it out. So again, I know how to calculate dm by d alpha if I know dynamic pressure, area, mean aerodynamic chord, and derivative Cm alpha, right, which is also linked to static margin. You remember that, okay? Because roughly we remember dCm by dCl is approximately equal to minus static margin, right? So you can easily find out dCl or dCm by d alpha using this, right? Because dCm by d alpha I can write as dCm by dCl into dCl by d alpha, which is nothing but Cl alpha, and dCm by dCl is nothing but static margin, 10% static margin, 5% static margin, 15% static margin. So all these things are known to a designer before he starts the design, and is a typical number, okay? So we are comfortable in finding expression for alpha derivatives. In the next class, we will go for alpha dot and q and delta derivatives. Okay? Thank you very much.